Thank you for coming. My name is Hernan, and this is Agustin. Yep. And as you can see, the name of our presentation today is Understanding the Windows SMB NTLM Authentication with NAND Vulnerability. So basically, the idea of the presentation is to describe this vulnerability in detail, to explain and demo 3 different techniques that we developed to exploit this vulnerability. We are also going to clarify some misconceptions that I think people have about this vulnerability. We are also talking about the scope, the severity, and the impact of this vulnerability, because I also think that that is not very clear. Also, I think that if you have read the advisory published by Microsoft, some of the things that are there, I don't want to say are not accurate, but not the whole history is there. And finally, we're going to pretty much make a summary of the things that we describe through the presentation, and share some things that I think, some security issues that we can be reminded of by this vulnerability, and that perhaps you can apply in the future when analyzing similar protocols like NTLM. Basically, this vulnerability is not just one vulnerability, but consists in a series of flaws in the way that Windows implemented the NTLM authentication protocol. An attacker that can exploit these flaws can access the SMB service without any kind of credentials, and once he has done that, he can gain read-write access to files, gain access to any kind of resource that is being shared using SMB, and also execute code remotely by using DCE RPC over SMB. We published this vulnerability at the beginning of this year, and we also published an advisory at that point in time, and there is a patch already for this vulnerability. So why do we think that it's worth talking about this vulnerability? Well, basically, the flaws that we found in the implementation of NTLM, that is basically the most widely used authentication protocol in the world, have been there for not only 14, actually 17 years. So this basically means that since Microsoft shipped the first version of Windows NT, and that is Windows NT 3.1, up until February of this year, the NTLM authentication protocol has been seriously flawed. So if you have been worried about attacks such as SMB relay, or also known as the SMB credential reflection attack, or pre-compute dictionary attacks against NTLM version 1, well, I think that this is basically worse than that, because the protocol implementation was flawed, allowing for other attacks that are more dangerous than those ones. And this flaw, like I said, affects all versions of Windows, from Windows NT 3.1, NT 4, 2000 XP, 7, 2008. All versions were vulnerable. Besides that, we also think that from a technical standpoint, this is kind of an interesting vulnerability, because we're not talking about something that is more common to find nowadays, like buffer overflows, integer overflows, or things like that. But this vulnerability or series of flaws has to do with issues in the pseudo-random number generator used by the implementation of NTLM, that we think is pretty interesting. It's not something that you find all the time. And also other implementation issues that we found in the protocol that allow for side-channel attacks that can result in, for example, replay attacks, and also an attack that also we think that by itself is very interesting, that is the possibility of predicting challenges. And we're going to see what all this means. So in order to understand the flaws, you need to understand how NTLM works. NTLM is basically a protocol that belongs to a family of protocols that are called challenge response authentication protocols, or perhaps cryptographic challenge response authentication protocols. So what is a challenge response authentication protocol? Well, the idea is pretty simple. You have a client that wants to authenticate against a server. The client wants to prove to the server that he is who he says he is. Both entities, the client and the server, share a secret, for example, a password. And the client wants to prove to the server that he knows the secret, in this case, for example, the password, but without actually sending the password. Otherwise, we will be talking about something like the telnet service where you are sending the password. And we're trying to avoid that. We're trying to avoid revealing the password, because we are doing all this over a channel that is not encrypted at all. So how you do that? The solution proposed by the channel response protocol to this problem is to, every time that the client wants to authenticate against the server initiates an authentication attempt against the server generates what is called a challenge, the client receives that challenge and performs some kind of computation, applies a function or an algorithm to that challenge and to the secret, takes the result of that calculation, sends that result to the server applies the same function or algorithm to both the secret and the challenge, and if the results match, that means that the client knew the secret. And the secret, that in this case could be the password, was actually never sent to the server. One thing that is very important about this whole scheme is that the challenge, that is usually a number, has to have certain properties. If the challenge does not have these properties, the whole protocol falls apart. The security of the protocol breaks. Once some of these properties that the challenge needs to have, the challenge is usually a number, and this number needs to be non-predictable. For example, if the challenges are 1, 2, 3, then 4 and 5, that's predictable because you know that the next challenge is the previous one plus 1, so that's not good. Also, the challenge has to be a unique number. If you, for example, issue the numbers 1, 2, 20, 19, 2 again, you don't want that because that also breaks the protocol. So those are very important things that the protocol have to adhere to. If these properties are not met by the challenge, that is usually called a nonce, hence the name of the vulnerability, some attacks can happen. For example, if the server generates duplicate challenges, that is, generates the same challenge over and over again in a short period of time, what an attacker can do is just, if the attacker is able to eavesdrop the communications between the client and the server, he can just look at the traffic without knowing nothing, just look at the traffic and create a dictionary of challenges sent by the server and responses sent by the client. So he has like a dictionary where he has a column with nonces or challenges and a column with the responses. Just by having that, since the attacker knows that the server is going to issue duplicate challenges, what the attacker does is connect over and over again against the server until the server responds with a challenge that the attacker has seen before and that he has in his dictionary. So for example, in this case, the server issued the challenge, the number 2, the client issued the response 4, the attacker grabs that and saves that, and then the attacker starts performing authentication attempts against and again and again against the server until the server returns again the challenge 2, and at that point he replays the response that he has previously and can gain access. So that's the problem that can happen if the server generates duplicate challenges. The other thing is, for example, if the challenge is predictable, let's say that the attacker can predict when the server, at which point in time the server is going to generate certain challenge, that is a number. So by knowing that, the attacker actually uses the client, forces somehow a connection from the client to the attacker to obtain the corresponding response for that challenge. So now the final step is the same as before, but this time the attacker connects at the exact time that he knows the server is going to generate the challenge that he predicted, and at that point sends back the response that he got from the client and gains access. If we take a look at NTLM, it works exactly like this generic example. Here you can see a typical NTLM version 1 authentication communication. For example, when the client wants to communicate with the server, the client sends an SMB negotiated protocol request packet that initiates the authentication attempt. The server responds with the challenge, that in the case of NTLM is an 8-byte long challenge or nonce. The client sends back a response. We don't care for our purposes how this response is actually calculated, but as you can see, it includes the username, the domain, and the hashes of the password. That would be the secret in this case. The server performs the same calculation that the client did to send back the response, since he also knows the hashes of the password of the user. And if everything matches, allows or disallows access to the client. So here you can see a typical example of an NTLM version 1 authentication process, basically so you can actually see what goes over the wire. You can see the challenge in red over there sent by the server, and in the bottom of the slide you can see the response sent back by the client. If we take a look at NTLM version 2, it's practically the same. The only thing that changes is how the client calculates the response that is sent back to the server. But pretty much it works the same way. Again, a typical example of what you will see over the wire, the challenge generated by the server and the response sent back by the client. So, since this is a channel response authentication protocol, the nonces generated by the server, need to have the properties that I said before when I was talking about the generic example of a channel response protocol. It needs to be non-predictable and needs to be unique. Otherwise, we have a problem. So basically the thing is, if you connect over and over again against a Windows server, you should expect that the server will return a nonce that is non-predictable and always a different number. Well, the first flaw that we found actually was that the server was returning repeated challenges. And that's a big problem because that is breaking the security of the protocol. And not only that, it was not returning duplicate challenges, but it was doing so in a very short period of time. Because it's not the same thing if you get a duplicate once a year, for example. But if you get a duplicate once every 2 seconds, for example, that's a bigger problem because you can do all the attacks that I talked about when talking about the generalities of a channel response authentication protocol. So basically, Agustin here is going to show you some plots that we did that are trying to show you how often, how many, and how are the nonces generated by a Windows server that is vulnerable to this vulnerability.
Hi. So we wanted to have a visual idea of how often the server was generating duplicate challenges. So we perform multiple connections to the server and save all the challenges. So we saved a sample of 64K samples, and we try to plot them. So we counted the number of occurrences of each challenge and plotted it in a graph. So for example, this is the first 4K sections of the sample, where there are only unique challenges, so they are plotted at number 1. And if the challenges are duplicated, they will plot at number 2, for example. This is the first 8K section of the sample, where we can see duplicates. And here, this is the first 16K of the sample, where we start observing 3 times issued challenges. And this, for example, is the whole sample, where we can see how the duplicates line is getting thicker, mimicking the unique challenges, for example. So going back to the 16K sample, we can see some kind of small pattern duplication. There are 4 little dashes there that I want to know what's happening there, so I have to visualize each duplication in a separate way. So we plotted that in a different way. We assign to each duplication of the challenge a unique ID, and we plotted the pairs. So if we imagine